We're doing expectations in moments. We already did a couple examples. Here's yet another example. Here's a joint PDF. And I won't go through this again, but in previous videos, we found these conditional PDFs. And let's just take these on faith for now, but they were derived in a previous video. Problem here is to find the mean and variance of x given y is some value. The way we do that, here's what we're looking for. The expected value of x, because that's the mean, but it's a conditional thing, given y equals a half. We do that like the other expectations. It's going to be x times the PDF, but in this case, it's a conditional PDF. And that was just this constant between these limits. So it's just this square root of 3 over 3 times x over a symmetric interval. So the mean is just 0. And if the mean is 0, then the variance is just the mean squared, the second moment. So the variance is the mean square now because the mean itself was 0, given y equals a half. So now it's x squared times that PDF, square root of 3 over 3. This is an even integrand, so we can integrate from 0 to the upper limit if we multiply by 2. So we can pull the constant stuff out, multiply by 2 because of that, because it's even, and we're only going to integrate from 0. Bada boom, bada bing, it's 1/4. The variance is a 4th. For this PDF, find the mean, square, and variance. Okay. There's several ways to do this. The mean is this integral, right? X times this PDF, we only integrate over positive x's. You could use integration by parts, kind of a pain. Both of these, you can do it. It's kind of a pain. You got to do integration by parts. It's just a integration exercise. Or you could say, I'm just going to cheat a little bit and use the table and things in the table, and from there you can find it again. Let's see again. Here's what the mean is. You can write that down from this. Here's what the mean square is. So this is all about taking these two integrals. And here's the point of going through that. The Laplace trick, I call it. Here was the Laplace transform. Take the Laplace transform of a function and put it in this integral. That's the Laplace transform. I could change the t's to x's. In this case, here's the integral we want to take. Or I could change the x's to t's. I'm going to integrate it out. So it looks more like a Laplace transform thing. But let's change the x's to t. So we're still taking this integral. Well, if you look at it, that's the Laplace transform of t, where s is just 1. So if you know Laplace transforms, the Laplace transform of t is 1 over s squared. Plug in s equals 1, you just get 1. That was a lot easier than integration by parts or looking it up in the table. Similarly, for the mean square, there's an x squared there. Put it in terms of t, it's like this. And again, that's like the Laplace transform of t squared. Again, evaluated at s equals 1 here. T squared is 2 over s cubed. At 2, there we get the variance. So that was introducing the Laplace trick. I think I'll save this for another video, but we'll use the Laplace trick and kind of examine the Rayleigh distribution in some depth. I'll save it